There's a common refrain that we can just move to Mars, as if it were some kind of cosmic backup planet. But have you ever truly stopped to ask if a human being could actually survive there even for a moment? In this video, we're going to examine what Mars really offers a human body and trace the facts to a harsh and unavoidable conclusion. If you see the red planet as humanity's escape route, then what follows might change your perspective entirely. Mars is often framed as our future home, but the first critical problem has nothing to do with rockets or settlements. The planet simply has no air you can use. On Earth at sea level, the atmosphere presses down on you with about 100,000 pascals of force. This is what we call one standard atmosphere. It's the environment your body is built for. On the surface of Mars, that pressure drops to just 600 pascals, which is less than 1% of Earth's. To feel that here, you'd have to be 30 kilometers high, or about 100,000 feet up. No person can survive unprotected at that altitude. In such a low-pressure environment, the air is so thin that your lungs can't draw in enough molecules to function. You simply cannot breathe. And while your internal body pressure would prevent your blood from boiling, any exposed fluids like the moisture on your tongue would begin to bubble and turn to vapor. Your eyes would dry out instantly. Your chest would feel as if it were collapsing. You would lose consciousness within seconds, and death would follow moments later. There is no option to just hold your breath and sprint back to safety. The problem isn't simply the lack of oxygen, it's the near total absence of atmospheric pressure. On Mars, stepping outside without a pressure suit is not an act of courage. It is instantly fatal. You would need a specialized suit that wraps your body in a miniature Earth-like atmosphere, maintaining that crucial pressure and shielding your internal fluids from the vacuum outside. This suit is not a convenience. It is a mobile life support system, and it must work perfectly every single second. A faulty seal, a cracked valve, or a torn glove would cause the pressure to equalize, which means the air inside your suit and your lungs would rush out violently. You might argue then that the solution is to stay indoors. We could build robust habitats, pump the Martian air inside, and compress it to a comfortable pressure. That sounds simple enough until you ask a very basic question. What is that Martian air actually composed of? Here on Earth, our atmosphere is about 21% oxygen, the gas our bodies use to convert food into energy. Most of the remainder is nitrogen, which is largely inert when we breathe it. The atmosphere on Mars, however, is about 95% carbon dioxide. Oxygen accounts for roughly 1/10 of 1%, an amount that is, for all practical purposes, zero for human respiration. If you were to fill a room to Earth-like pressure using nothing but the Martian atmosphere, you would not have a sanctuary. You would have a chamber filled with a gas your body cannot process, containing only the faintest trace of what you actually need. But the problem is worse than a simple lack of oxygen. Carbon dioxide itself is toxic at high concentrations, and your body is exquisitely sensitive to it. Here on Earth, even a small rise in CO2 levels can make a room feel stuffy, causing you to breathe faster as your heart rate adjusts. At a concentration of just a few percent, you can experience headaches, confusion, and even panic. At 10%, you would lose consciousness in minutes. Mars takes this dangerous gas and makes it the very substance of its atmosphere. To make the air breathable, then, you can't just pump the atmosphere indoors and increase its pressure. First, you would need to scrub nearly all of the carbon dioxide out of it, a process that requires storing or venting the toxic gas. Then you would have to add oxygen, either by shipping it from Earth or by manufacturing it on site with energy-hungry machinery. This requires a constant, large-scale industrial operation just to keep the air in your habitat safe. If that system falters, if it breaks down or the power fails, the air quality inside would quickly drift outside the narrow band required for human health. This brings up another question. Since the atmosphere is so rich in carbon dioxide, could we at least use it along with any available water to easily grow plants? And could we tap sources of liquid water on the surface to help make that happen? That sounds like a logical next step, but on Mars, even water itself behaves strangely. The surface pressure is so low that water struggles to remain in its liquid state. For instance, if you poured a puddle of water onto the ground at a mild temperature, somewhere between 0 and 20 degrees Celsius or 32 and 68 Fahrenheit, it wouldn't remain stable. It would simultaneously begin to freeze and to boil, turning directly into ice and vapor despite the temperature being well above freezing. The physics of the environment forces water into one of two states, solid or gas, with very little room for liquid in between, especially out in the open. As a result, you won't find the natural lakes, rivers, or rain that we depend on. So when you hear that Mars has water, that statement is true. But nearly all of it is locked away as ice, buried underground or frozen into the soil. To get usable liquid water, you would have to mine that frozen earth, heat it to melt the ice, and then purify it to remove any contaminants. This is an energy-intensive industrial process that must run constantly, day after day, just to produce what flows freely from a tap on Earth. A water source on Mars, then, isn't a lake you can stroll to with a bucket. It's a production system. It involves drills, heaters, pumps, filters, and storage tanks, all connected to a power grid. If any part of that chain fails, your water supply fails with it. And because liquid water is so unstable in the open, it must be kept contained at all times within pipes, tanks, and pressurized buildings. It's never truly free, and it's never part of a natural cycle. At this point, you might throw your hands up and say, "Fine. We won't use the Martian atmosphere at all. We'll just generate our own perfect mix of gases inside sealed habitats." Surely then you'd be safe. The answer is you would be safer, but you would still be living on a knife's edge. Your body, your lungs, your sinuses, the delicate blood vessels in your head evolved under Earth's very specific conditions, with a precise pressure and a precise mix of oxygen, nitrogen, and other gases. In a Martian habitat, you are asking your body to place its entire trust in machinery to maintain that narrow band perfectly. A minor malfunction in the carbon dioxide scrubbers, a stuck valve, or a miscalibrated sensor could subtly shift that balance without you even realizing it at first. You might just feel tired or get a headache, or feel a strange sense of anxiety. By the time you recognize that the air itself is the problem, the levels could already be dangerous. On Earth, if a building's ventilation system fails, you can simply open a window and let the outside air rush in to fix the problem. On Mars, opening a window is not an option because the air outside will kill you even faster. The planet provides no safe default. Its natural state is a thin, toxic, low-pressure gas that your body cannot use on a surface that cannot support liquid water. The only reason you would be alive is because your machines are in a constant, active battle against that reality. Every breath you take on Mars would depend on a network of compressors, filters, pumps, sensors, and software, all working correctly, all with redundant parts, and all maintained by people who are themselves dependent on that very same system. When the atmosphere is that unforgiving, when water is that difficult to obtain, and when there is no natural safety net outside your walls, the question becomes incredibly sharp. What happens when you place this fragile, artificial bubble of life onto a world that is also brutally cold? A world where extreme temperature and pressure swings batter your equipment every single day? You've already seen that Mars offers no usable air. Now let's add another layer. The planet is also cold on a scale that both your body and your technology were never designed to handle. And that cold is relentless. The average temperature on Mars hovers around -60 degrees Celsius, or about -76 Fahrenheit. That isn't just a harsh winter's night. That is deep freezer territory, planet-wide. At the poles in the dead of winter, it can plunge below -120 Celsius. That's -184 Fahrenheit. This is colder than most laboratory freezers used to preserve biological samples. It's a temperature where rubber becomes brittle and standard lubricants fail. So before you even begin to imagine cities, you have to grasp this fundamental truth. You would be trying to sustain human life and operate delicate machinery on a world that is naturally set to the temperature of an industrial refrigerator. You might think, well, we'll just insulate everything. We know how to handle the cold. But the coldest places on Earth are temporary and localized. On Mars, the deep cold is permanent and global. Any exposed metal, seals, cables, or joints would be subjected to that extreme cold for years on end. And they wouldn't just be sitting there. They would be constantly cycling as the temperature rises during the day and plummets again at night. Materials expand when they warm up and contract when they cool down, and each material does so at a slightly different rate. This means that every single Martian day or sol, your structures would essentially breathe in and out. Tiny mechanical stresses would build up, and micro cracks would begin to form in places you can't even see. Now let's consider the nice parts of Mars near the equator, where conditions are supposedly more hospitable. In direct sunlight on a good day, the temperature there can climb to around 20 degrees Celsius, or 68 Fahrenheit. That sounds almost pleasant. But by dawn, that very same spot can plunge to minus 70 Celsius or minus 94 Fahrenheit. That is a temperature swing of 90 degrees Celsius, 160 degrees Fahrenheit, in less than 24 hours. And this doesn't happen just once. It happens every single sol, day after day. On Earth, if you were to fly from a hot desert directly to the middle of Antarctica, you would feel that shock. Your body would register that an extreme change had occurred. On Mars, your habitat walls, your pipes, your vehicles, and your spacesuits would have to endure that kind of thermal shock constantly in place with no relief. The seals on your airlocks, the windows of your pressurized modules, the joints on your rover, all of them would be expanding and contracting on a daily cycle. Over months and years, this is a recipe for wear, fatigue, and eventual failure. Unless every single component is over-engineered with massive safety margins, extra weight, and a rigorous inspection schedule. You might then suggest that while the temperature swings are extreme, the thin atmosphere might slow down the rate of heat loss, making it feel more like being high up on a mountain. That sounds plausible, but it's dangerously incorrect. On Mars, the air is too thin for convection to be the primary way you lose heat. Instead, two other processes dominate: radiation into the blackness of space and conduction into the frozen ground. Your habitat, your suits, and your vehicles would all be sitting on a frigid surface under an equally frigid sky, constantly bleeding warmth through infrared radiation and direct contact. So your spacesuit isn't just trying to keep air in. It's also in a constant battle to keep heat in, fighting against a universe that is effectively just a few degrees above absolute zero. The regolith beneath your feet, that dusty, rocky soil, acts as a massive thermal sink, pulling warmth out of anything it touches. The result is simple. The amount of power required just for heating would be enormous. To keep a habitat at a comfortable 20 degrees Celsius, while the environment outside is minus 60 or colder, you would have to run heaters non-stop. You would be burning through electrical energy around the clock simply to maintain room temperature. And if your power were to fail, the temperature inside would begin to drop toward the lethal cold outside much faster than you might expect. Consider what this means in an emergency. On Earth, if a house loses power in the winter, it cools slowly, often over many hours. You have time to put on a coat, call for help, or go somewhere else. On Mars, if you lose power in active heating, the extreme cold is so direct and relentless that your habitat could become unsurvivable in a terrifyingly short amount of time. The same holds true for any pipes carrying water, waste, or breathable air. They could freeze solid and burst, leaving you to deal with both a mechanical failure and a life support breach at the very same time. Now add one more layer to this, something entirely unique to Mars. During the winter, especially near the poles, the carbon dioxide in the atmosphere actually freezes out of the air and falls as frost or snow. The main gas of the atmosphere itself turns into a solid on the surface. When this happens, the total amount of gas in the atmosphere decreases, causing the planet's air pressure to change. Then, in the spring, that frozen carbon dioxide warms up, sublimates directly back into a gas and re-enters the atmosphere. So every Martian year, the planet literally breathes, as a portion of the atmosphere freezes solid during the winter and turns back into gas in the spring. The global air pressure rises and falls. For anyone trying to build a lasting presence on Mars, this is not just a scientific curiosity. It is a profound engineering challenge. When carbon dioxide frost accumulates on the surface and then sublimates away, it can move dust, crack the ground, and shift surface loads. This creates a phenomenon known as frost heave, where the soil swells and then settles. Structures in the higher latitudes would need foundations engineered to endure this slow, seasonal flexing. Any pipelines or cables laid across this shifting ground would be subjected to constant stress, risking eventual failure. The pressure changes have their own implications. The near vacuum outside your habitat is not even stable. It fluctuates with the seasons. This means your habitats and suits, which are built to withstand a specific pressure difference, must contend with a moving target. All the automated systems that monitor external pressure to control valves, airlocks, and emergency vents would have to account for this variation year after year without error. When you put all of this together, one fact becomes undeniable. The baseline state of Mars is a deep freezer. The daily pattern is one of violent temperature swings. The ways you lose heat are harsh and unforgiving, and the atmosphere itself freezes and thaws on a schedule that physically alters your surroundings. You wouldn't just be building a town in a cold place. You would be fighting the planet's fundamental thermal nature every single hour, just to remain within the narrow band of human comfort. And remember, you would be doing all of this on top of the problems we've already covered. An atmosphere that is useless to you, water that doesn't exist in liquid form, and a total dependence on a chain of machines that can never be allowed to fail. This leads to another question. Even if your technology could perfectly manage the pressure, the temperature, and the air chemistry, what would happen to a human body that has to live for years in a gravitational field that is only 38% of what it was designed for? Our bones, muscles, and organs are all tuned to operate at 1 G. On Mars, they would be forced to function permanently at just 0.38 G. You might think weaker gravity would make life easier, less strain on your joints, the ability to leap effortlessly. It sounds like a dream, right? But while that lower gravity might feel like a benefit at first, over the course of years, it would quietly dismantle your body in ways we don't yet know how to prevent. On Earth, you live under what we call 1 G of gravity, the force that gives you weight, strengthens your bones, and even helps position your internal organs. Mars offers only 38% of that, or 0.38 G. To put it in numbers, Earth's gravity accelerates you downward at 9.8 meters per second squared. On Mars, that pull is just 3.7. This means that while your mass would be the same, a person weighing 70 kilograms on Earth would feel as if they weighed only 26 kilograms, about 57 pounds on Mars. That might sound enjoyable until you consider what happens to bones and muscles that are never, ever again put under their full normal load. Our best data comes from astronauts in microgravity orbiting the Earth. Without intensive exercise, they can lose 1 to 2% of their bone mass every month. Their muscles, particularly in the legs and core, begin to atrophy. Their spines can even lengthen slightly, which sounds interesting until you realize it often leads to back pain and problems with spinal discs. But that's in 0 G. On Mars, you aren't floating, but you aren't standing under 1 G either. You exist in a permanent in-between state, where your skeleton is underloaded every second of your life. And the fundamental problem is that no one truly knows what decades at 0.38 G would do to a human spine, to the hips and knees, or to the cartilage that evolved to bear our full earthly weight. Perhaps bone loss would slow down but never fully stop. Perhaps joints would remodel themselves in harmful ways, or spinal discs would degenerate more rapidly. You would be asking a body tuned by millions of years of evolution for 1 G to simply adapt to a new normal. The current plan essentially is to find out once we get there. That is not a safe approach when evacuation is nearly impossible and medical facilities would be at best rudimentary. The effects would extend beyond the skeleton. Consider your heart and circulatory system. Here on Earth, gravity constantly pulls fluids down toward your feet. Here on Earth, gravity is constantly pulling fluids down into your legs and feet. Your entire circulatory system, your heart, your blood vessels, the tiny valves in your veins, is designed to work against that downward pull. In the zero gravity of the International Space Station, the opposite happens. With no down to pull them, fluids drift upward into the chest and head. This is why astronauts often have puffy faces, congested sinuses, and thin legs. Over months, this fluid shift can even change the shape of the heart, and for some cause vision problems due to the altered pressure around their eyes. Mars would place your body in a condition that no human has ever experienced long-term. You're not at full weight, but you're not weightless either. Fluids would still shift upward more than on Earth, but less than in orbit, creating a blood pressure environment your body has never encountered. Perhaps you'd live with a constant feeling of congestion. Perhaps your heart muscle would slowly remodel itself to pump against this weaker force. Perhaps your ankles would never feel the familiar pressure they do on Earth. The result could be chronic swelling, permanent changes to your heart's rhythm, and a new class of cardiovascular illnesses that are completely unknown to medicine. For an average adult, your entire circulatory system is engineered to manage a column of fluid about 1.8 meters tall under 1 g of force. Mars would permanently rewrite both that geometry and the force acting upon it. This means that all our medical knowledge, every diagnostic chart, every risk assessment, would become guesswork because the fundamental physics your body operates under would have changed. And that leads to the truly difficult question. The question isn't just whether an adult can survive on Mars. It's what would happen if you tried to raise a child there. Experiments on animals in simulated low-gravity environments already reveal serious developmental problems. Bones don't form correctly. Muscles fail to develop their proper mass. The inner ear, which governs our sense of balance, calibrates itself exclusively for that weaker gravity. Now imagine a child born and raised entirely at 0.38 g. Their entire body, their bones, muscles, and nervous system would accept that weaker gravity as its baseline. Their spine would develop under a lighter load. Their hip joints would never strengthen enough to support their weight on Earth. Their heart and blood vessels would adapt to pumping against a much weaker downward pull. If that person were ever brought to Earth, our 1 g of gravity would feel crushing. Every step would be a struggle, as if they were carrying a heavy weight they could never set down. It's entirely possible their skeleton and organs simply couldn't withstand the strain, not without intensive medical intervention, if at all. In this scenario, humanity wouldn't become a flexible, multi-planet species. Instead, we could split into different versions of human, unable to live in each other's gravity wells. People born on Mars would be trapped there, not by the cost or the distance, but by their own biology. This isn't the science fiction dream of a civilization that roams the stars. It's the reality of separate, gravity-bound branches of humanity. The immediate response to this might be to propose a simple solution: more exercise. After all, we know that rigorous workouts help astronauts mitigate bone and muscle loss in orbit. Yes, exercise helps, but the low gravity on Mars sets a hard limit on how much weight you can naturally put on your body. That 70-kilogram person who weighed 154 pounds on Earth now feels as if they weigh only 57 pounds. When they do a simple bodyweight squat, their bones and muscles are only experiencing that reduced load. To replicate the stress of an Earth workout, they would have to add significant extra weight or use machines that actively push or pull against them. On Earth, you get resistance for free just by standing up. On Mars, you would have to artificially engineer it back into every activity. This would mean wearing exoskeleton suits that pull you down, using treadmill harnesses with powerful springs to keep you from floating off the belt, and relying on resistance machines to stress your joints in ways that walking around simply wouldn't. To truly mimic Earth's conditions, You would likely need centrifuge gyms, rotating rooms that spin you around to simulate higher gravity while you exercise. All of this means more equipment, more power consumption, more maintenance, and more points of failure just to keep your skeleton from slowly dissolving. And there's a catch. If you push too hard with these artificial loads on a body that has already lost bone density or whose joints have begun to change, you risk causing fractures, torn tendons, and spinal injuries. So the training regimen would have to walk a razor's edge, hard enough to prevent bone loss but gentle enough not to break people. And all of this would take place inside a sealed habitat, on a planet where emergency surgery and rehabilitation are severely limited. So let's add this all up. Living on Mars means your bones would be permanently underloaded. Your heart and circulatory system would exist in a strange, untested state. And any children born there might adapt so completely to 0.38 G that they could never safely return to the world their family came from. You wouldn't just be building a settlement. You would be committing your body to a lifelong, uncontrolled biological experiment. And remember, all of this would be happening while you are already battling a thin, toxic atmosphere, extreme cold, and a complete reliance on fragile life support systems. Now let's layer one more threat on top of all that, one you can't see or feel, but one that would bombard every cell in your body every single hour. This is the threat of radiation, which on Mars streams down from the sky and arrives right at your doorstep. Here on Earth, we live beneath a powerful shield that we rarely even think about. On Mars, that shield is almost entirely absent. The harsh environment of space isn't far away. It extends all the way down to the ground you walk on. Earth has two primary layers of protection, a thick atmosphere and a powerful magnetic field. Together, they block or deflect the vast majority of high-energy particles arriving from the sun in deep space. Mars has almost no global magnetic field and only a whisper-thin atmosphere. The consequence is that what we call space radiation doesn't stop high up in the sky. It penetrates all the way to the surface, striking your habitat, your rover, your suit, and your body. First, there is the constant background radiation, known as galactic cosmic rays. These are highly energetic particles originating from far beyond our solar system, and they arrive in a steady, unending stream. Measurements taken by the Curiosity rover show that a person on the Martian surface would be exposed to between 0.2 and 0.7 millisieverts of radiation every day. For comparison, an average person on Earth absorbs about 3 millisieverts from natural background sources over the course of an entire year. This means that in just 5 to 15 days on Mars, you would receive the same radiation dose you'd normally get in a full year back home. Over the course of a single Martian year, your total exposure would be somewhere between 25 and 80 times your typical annual dose on Earth. And that's not even counting the radiation from major solar storms. So what does this actually do to your body? This level of radiation doesn't cause immediate sickness, but it steadily damages your DNA. It creates tiny breaks and chemical changes that your cells must constantly work to repair. Your body is good at this, but it isn't perfect. And over time, the errors accumulate. The long-term consequences include a significantly higher risk of cancer, potential damage to your bone marrow and nervous system, and possible harm to your heart and blood vessels. On Earth, our atmosphere and magnetic field neutralize much of this threat. On Mars, you're taking a direct hit, and that's just on a normal day. The real danger comes when the sun becomes active. Solar particle events, massive flares, and coronal mass ejections can hurl clouds of energetic particles across the solar system. When these storms reach Earth, our magnetic field and thick atmosphere absorb the vast majority of the impact. On Mars, without that protective shield, those same particles can punch right through the thin atmosphere and slam into the surface. For a person inside a lightly shielded habitat or out exploring in a spacesuit, a strong solar storm isn't a beautiful light show. It's a serious medical emergency. In just a few hours, you could absorb a radiation dose equivalent to a full-body CT scan, or in a severe event, much more. At those levels, you would be at risk of radiation sickness, nausea, fatigue, and damage to your immune system, while adding a massive spike to your lifetime cancer risk in a single afternoon. If your storm shelter isn't properly shielded or if you can't get back to it in time, Mars offers no second chances. You cannot simply wait it out inside a thin-walled habitat and hope for the best. The obvious solution is to build proper shielding, but this is where the physics runs up against the brutal logistics of living on another planet. To effectively block radiation, you need mass, a lot of it, between you and the sky. Water is a good shield, as are dense plastics and, of course, rock and Martian soil. You would need, at a minimum, tens of centimeters of solid material. For truly robust protection against both cosmic rays and solar storms, you'd want to bury your habitat under 1 to 3 meters of packed Martian soil. Now, think about what that means for actually building a base. Let's say you have a small habitat, about 100 square meters. To cover that with just 2 meters of Martian soil, you would need to pile hundreds of tons of material on top of it. At 3 meters, you're looking at a load of well over 500 tons. That is not something you can move with a small rover. Your options are either to dig deep into the ground, creating tunnels and caves, or to build incredibly strong structures and then bury them under massive amounts of dirt. This reality immediately shatters the popular image of Martian cities with vast glass domes and open plazas. Transparent materials are generally poor radiation shields. You could not simply sit under a large window and consider yourself safe. A realistic settlement would look more like a buried bunker or an underground warren with perhaps a few small, heavily shielded viewing ports. Any time spent outside would be strictly managed. You would limit your exposure, meticulously track every person's accumulated dose, and treat every excursion as a controlled risk, not a casual walk. Even with all these precautions, the total radiation dose for a Mars mission would be brutal by earthly standards. A round-trip journey with months spent in deep space each way, plus a year or two on the surface, could easily expose an astronaut to a cumulative dose of 600 to 1,000 millisieverts. That is enough to meet or exceed the entire career radiation limit for many astronauts. This translates to a significantly increased lifetime risk of cancer, along with other long-term health problems we don't yet fully understand, particularly those affecting the brain. Now imagine extending that exposure from a 2 or 3 year mission to a 20-year life on Mars. You would have an entire population living under a constant slow-motion bombardment of their DNA, punctuated by the occasional high-intensity burst from a solar storm. Children, pregnant women, the elderly, and anyone with a pre-existing medical condition would accumulate this radiation dose year after year, with no easy way to return to the low-radiation environment of Earth. This is not comparable to living at high altitude, where radiation is only slightly elevated. Mars shifts the entire baseline into a different category. You can mitigate the risk with shielding, with underground habitats, and with careful planning, but you can never bring it back down to Earth-like levels unless you are prepared to spend nearly your entire life inside a heavily armored shell. And every single kilogram of that shielding would have to be mined, moved, and put in place by equipment that is itself being damaged by that same radiation. So let's put this all into context. On Mars, the air is thin and toxic. The low gravity is slowly pushing your skeleton and your heart into uncharted territory. And the environment is constantly bathing you in levels of radiation that Earth's natural shields have always protected you from. You are living in a bunker, buried under meters of dirt, tracking your radiation dose like a dwindling bank account, knowing that every trip outside is another withdrawal. And while all of that is battering your cells from above, another threat is waiting right under your feet. The planet's own dust, ground down into microscopic shards that will try to get into your lungs, your machines, and every gap in your life support system. You can build thick walls and bury your habitats under meters of soil, but one enemy on Mars will get through regardless: the dust. And this isn't just dirt that you can wipe away with a cloth. It is a substance that attacks your lungs, your equipment, and your life support systems all at once. The dust on Mars is exceptionally fine, with many particles measuring just a few micrometers across, roughly the size of the particulates in smoke. Because they are so small, these particles bypass the natural filters in your nose and throat. They travel deep into the smallest passages of your lungs, settling in areas from which your body has great difficulty clearing them. We've seen a preview of this danger before. Apollo astronauts returning from the moon's surface reported symptoms of lunar hay fever after inhaling the small amount of dust that was tracked back into their lander. That reaction came after just a few days of exposure. On Mars, you would be living for months or years in a habitat constantly vulnerable to tiny leaks and tracked-in contamination. Furthermore, the Martian atmosphere, as thin as it is still dense enough to keep this fine dust suspended. Unlike heavy sand on Earth, it doesn't settle quickly, it hangs in the air. It is picked up by the winds, works its way into the smallest cracks, and stays suspended for long periods. Every time an airlock opens, every time people cycle in and out, a fraction of that dust will come along for the ride. Filters can capture much of it, but no filter is perfect, and you would be living right next to the source. The chemistry of the dust makes it even more dangerous. Analysis from rovers and landers has revealed that Martian soil contains perchlorate salts, making up about 0.5% to 1% of its weight. Perchlorates are known to disrupt the thyroid gland, the part of your body that regulates metabolism, growth, and energy. Long-term exposure, even at low concentrations, is a serious health risk. If this dust contaminates your air, your water, or your food supply, you aren't just dealing with a harmless mineral powder. You are facing a slow chemical assault on your body. So when you hear people talk about growing food in Martian soil, the first reality check is this: you cannot simply add water and plant seeds. First, you would have to process it by the ton, washing it, chemically treating it, and flushing out the perchlorates and other toxic salts. Only after extensive testing could you even begin to think about agriculture. That process would require vast amounts of water, energy, and equipment just to create something that resembles the safe, fertile soil we get for free on Earth. The chemical toxicity is only half the problem. The physical nature of the dust is just as hostile. Here on Earth, grains of sand are often rounded and smoothed by wind and water over eons. On Mars, with no liquid water to smooth their edges, the dust particles are often sharp and jagged on a microscopic level. This makes them highly abrasive. They grind away at seals, moving parts, the joints of spacesuits, the wheels of rovers, and the surfaces of solar panels. Over thousands of cycles, this constant scraping wears things down, creating tiny grooves that can eventually become leaks. The low humidity and constant friction also mean the dust becomes electrostatically charged very easily. It clings to surfaces, your suit, your tools, your helmet visor, with the same frustrating persistence as styrofoam packing peanuts. But on Mars, this isn't just a nuisance, it's a hazard. After a single excursion, your entire suit would be coated in this fine, abrasive powder. When you re-enter the habitat, unless your airlock has a highly sophisticated cleaning system, some of that dust will inevitably come inside with you. Airlocks would become dust magnets unless they were designed as full-scale decontamination chambers, complete with high-pressure air jets, vacuums, and perhaps even electrostatic plates, all of which would consume more power and add more layers of complexity. Once inside the habitat, your only protection would be the filtration system. Your health would depend entirely on its performance. If the filters were brand new, properly installed, and rated for microscopic particles, you might be fine. But as those filters fill with dust, as their seals age, and as someone inevitably installs a replacement incorrectly during a rushed maintenance check, their effectiveness will drop. A small breach in the system wouldn't just mean a dirty room, it would mean the chronic inhalation of particles your lungs can't clear. Particles laced with perchlorates and other reactive chemicals. Over the long term, that points to a higher risk of chronic lung disease, inflammation, and cancer. It also puts additional strain on your immune system, which, remember, is already coping with radiation exposure, altered gravity, and psychological stress. Every spacewalk, every external repair, and every construction project would become a negotiation with the dust. You need people to go outside to build and maintain the base, but every time they return, you introduce a new round of contamination. Your machines would be fighting the same battle. Dust would get into bearings, gears, and electrical connectors. It would coat the radiators that are essential for shedding waste heat. Protective coatings that performed perfectly in clean labs on Earth might erode far more quickly than anticipated. Seals that endured thousands of cycles in testing could fail prematurely as abrasive dust is ground into them day after day. Solar panels would lose efficiency as dust settled on them, reducing your power supply and shrinking your safety margins for heating, filtration, and every other critical function. You could design systems to combat this. Robotic brushes, gas blowers, electrostatic repellents, but each one would be yet another complex subsystem to build, power, and maintain. The surface of Mars, then, is not a quiet, sterile desert. It is an active source of microscopic, sharp, chemically toxic particles that will relentlessly try to invade your lungs and your machinery. You cannot pave the entire planet. You cannot seal it out completely. You can only manage the rate at which it infiltrates your habitat and the effectiveness of your efforts to clean it up. And this threat is directly linked to the next. The dust isn't just sitting on the ground waiting for you to disturb it. The atmosphere, thin as it is constantly moving it, lifting it into the sky, sometimes just a few meters, sometimes tens of kilometers, and turning entire regions or even the entire globe into a dim reddish haze. A haze that blocks the sunlight and cripples your power supply right when you need it most. You're already contending with an atmosphere that wants to kill you, a gravitational field that's slowly dismantling your body, and a constant rain of radiation from space. Now add to that a planet whose weather system is uniquely designed to attack your power and your visibility at the same time. On Mars, you don't just deal with a little bit of dust. Storms can begin as small dust devils, then merge and grow until they encircle the entire planet. In some years, these global dust storms can rage for weeks. When that happens, the amount of sunlight reaching the surface can drop by 90% or more. Even on a clear day, Mars receives less than half the solar energy that Earth does, about 590 watts per square meter. When a global dust storm cuts that by 90%, the surface is plunged into a dim, copper-colored twilight day after day. The consequence of this is simple. Your solar panels effectively shut down. An array that looked perfectly adequate on paper will suddenly produce only a tiny fraction of its normal output. On Earth, a cloudy day might reduce your solar power, but you still get a usable amount. On Mars, during a global dust storm, the drop-off is catastrophic, and it can last for weeks. For this reason, the idea of living off-grid with solar power is a fantasy on Mars. Any settlement that relies primarily on sunlight must have massive energy storage and, more realistically, a nuclear power source as a backup. Otherwise, when the next global storm hits, your life support and heating systems will be running on borrowed time. You might assume that such dramatic storms would be accompanied by ferocious hurricane-force winds capable of tearing structures apart. But this is where Mars plays a trick on you. While wind speeds can reach around 110 kilometers per hour, about 70 miles per hour, the air is so thin that the actual force exerted is quite small. These winds are not going to knock down buildings or flip over heavy rovers. Instead, the real danger is more subtle. The winds are just strong enough and the air just dense enough to lift and suspend those fine dust particles. The planet's thin atmosphere becomes a delivery system, lifting dust from the surface, carrying it across continents, and depositing it on everything you value. The danger of the wind isn't that it will blow you over. It's that it will scour your equipment and blot out your sky. Now consider your hardware. Your radiators, solar panels, and thermal control systems are all designed with specific assumptions about how efficiently they can shed heat or collect light. When a layer of dust settles on a radiator, its surface properties change. It no longer radiates heat effectively. It starts to act like an insulator. Electronics that were designed to operate within a specific temperature range will begin to run hotter. At the very moment, you have less power available to actively cool them. Simultaneously, the dust coating your solar panels is crippling their efficiency. Your power generation collapses just as the strain on your thermal management systems increases. This means you can't just design solar panels, you have to design an entire dust management ecosystem to support them. You need mechanical brushes, gas blowers, or perhaps even electrostatic systems to shake or repel the dust from critical surfaces. All of this equipment must function reliably in low pressure and extreme cold, and it must endure for years while being attacked by the very same dust it's designed to combat, and every cleaning system you add consumes more of the power and requires more of the maintenance that you are already desperately short on during a storm. Then there is the problem of visibility. During the most severe global storms, the sky can become so opaque with dust that the horizon vanishes. The cameras on rovers and landers see nothing but a dim, orange fog. For a human crew, this means navigation becomes nearly impossible. Driving a rover would be treacherous. Landing new equipment would be incredibly difficult. Even simple tasks outside the habitat could become dangerous as you lose depth perception and familiar landmarks. When you can't clearly see rocks, slopes, or the lip of a crater, a single miscalculation can lead to a stranded or overturned vehicle, far from safety. During a major storm, your crew would likely be confined indoors for weeks. All outdoor activity would be suspended except in the gravest of emergencies. Construction would stop, crucial repairs would be delayed, all the while dust would continue to settle on everything and your power reserves would dwindle. You would be forced to ration energy, making impossible choices between heating, air recycling, water processing, and communications. On Earth, bad weather is an inconvenience. On Mars, it can bring your entire civilization to a halt. And the storms don't have to be global to cause problems. Even regional and local dust storms can drastically reduce solar power, clog your air filters, and scour your equipment. They also inject fresh dust into the atmosphere, which later settles as a fine layer over your entire base. So even in years without a planet-encircling event, you would be in a constant state of cleaning, monitoring filters, and watching your power output for the telltale signs that your solar panels are once again being choked by dust. There is also the matter of landing. A permanent presence on Mars depends on a steady stream of cargo and eventually people. But landing a spacecraft through a dust-choked atmosphere is extremely difficult. Your radar and optical sensors need a clear view of the ground. Your descent engines have to contend with blowing dust, and your landing site has to remain predictable as the surface shifts. A bad storm arriving during a critical landing window would add yet another layer of risk to an already perilous operation. So, let's put it all together. The Martian weather doesn't just make things a little more difficult. It directly attacks your primary source of power. It causes your electronics to overheat. It blinds your navigation systems, and it forces you to halt all surface operations at the very moment your equipment needs more attention, not less. You would be trying to run a high-tech outpost on a planet where the sky periodically turns down the dimmer switch on your entire energy grid. And think about the next link in the chain. While the storms are cutting your power and coating everything in dust, you still need a constant supply of water. For drinking, for recycling air, for growing food, and for manufacturing rocket fuel. And that water isn't waiting for you in lakes or rivers. It's locked away as ice in the frozen ground. And you have to dig it up and melt it using the very energy the storms are taking away. People often say that Mars has water as if that solves the problem. What they fail to mention is how incredibly difficult it is to turn that water from a notation on a map into something you can actually drink or use. Most of the accessible water on Mars is locked up as ice, and much of that ice is located in places that are ill-suited for human settlement. The clearest, shallowest deposits are found in the high latitudes near the poles. But those regions are also colder and darker for much of the year, making them incredibly difficult to power. The ideal landing zones you see in concept art, the flat lower latitude plains, tend to have their water buried deep beneath a layer of dry soil mixed with dust and salt. So you wouldn't be drilling a well into a liquid aquifer. You would be running a full-scale mining operation for frozen, salty mud. This would require excavators, drills, heaters, and conveyors, not to extract precious metals, but just to get water. Every kilogram of dirt you dig up would contain only a small fraction of ice, and you would have to repeat this entire process day after day because your crew, your life support systems, and your crops would have a constant, unrelenting need for water. Now consider the energy required. Let's say the ice in the ground is at a temperature of minus 80 degrees Celsius. That's minus 112 Fahrenheit. To turn that into usable liquid, you first have to heat it to 0 degrees, then you have to melt it, and then you have to keep it from refreezing while you purify it. That is a massive temperature change. When you do the math, you find that you'd have to spend hundreds of kilojoules of energy for every single liter of water you produce. A single liter might not sound like much, but a small outpost with a handful of people, a few crops, and some basic industry could easily require hundreds or even thousands of liters every day. Drinking, sanitation, oxygen production, agriculture, industrial processes, it all adds up. Multiply those hundreds of kilojoules by 1,000 liters, and you've just committed a huge portion of your daily power budget to the simple task of turning frozen dirt into clean water. And that's before you even factor in the energy consumed by the machinery itself. The drills, heaters, pumps, and purifiers all have their own inefficiencies. Heat leaks into the surrounding ground and radiates out into space. Energy is lost to mechanical friction. On Earth, our water systems often rely on gravity and natural pressure. On Mars, every step of the process must be driven by electricity. Then there is the problem of the water cycle. Here on Earth, we have rain, rivers, lakes, and oceans, all part of a closed loop. If you spill a glass of water, it eventually evaporates and re-enters the cycle. On Mars, the natural water cycle is almost non-existent. Ice sublimates directly into vapor, which can then condense as a thin layer of frost. Over geological time, some of that vapor simply escapes into space, lost forever. So when you lose water on Mars, it isn't just a local plumbing problem, it's often a permanent loss. Every time you vent moist air, dump untreated wastewater, or fail to fix a leak, you are not just running up your utility bill, you are shrinking your total water inventory. There is no ocean-sized reservoir, no natural replenishment. Your colony's water supply would be like a bank account with a very slow income stream and countless ways to overspend. Every kilogram you waste is a kilogram you might never get back. And even after you've melted the ice, you still have to deal with the chemistry. The ice and the soil on Mars are laced with perchlorates and other toxic salts. This means you can't assume that melted water is safe to drink. You would need a full-scale water treatment plant running 24/7. This would involve filtration to remove suspended particles, chemical processes to neutralize the perchlorates, and likely multiple stages of purification to produce potable water. So now, in addition to mining and melting, you are also running a continuous water treatment facility with its own pumps, filters, reaction tanks, sensors, and control software, all of which must operate without failure or contamination. Filters will clog and need to be replaced. Chemical agents will be consumed and need to be replenished. Tanks will need to be cleaned. Sensors will drift and require recalibration. Every step of the process will consume spare parts and power, and every maintenance task will introduce the risk of human error. Now consider what happens when something goes wrong. If a dust storm cuts your power, you might have to throttle back the heaters and pumps for your water system. This means you'll have to start rationing. At first, you might cut back on washing or industrial uses, but eventually you'll be forced to cut into your life support margins. If a part of the treatment system fails, you'll face a different, equally grim choice. Use partially treated water and accept the health risks, or shut down the supply entirely and race to fix the problem before your reserves run dry. And remember, you can't just have more water shipped from Earth. The cost of launching a single kilogram of water is astronomical. Over the long term, shipping water is not a viable solution. You are completely dependent on your ability to extract and recycle it locally under the harshest of conditions, with equipment that is constantly being stressed by cold, dust, and radiation. Recycling can help, but even the most advanced closed-loop systems are not perfect. You will lose some water to leaks, to vented air, to irreversible chemical reactions, and to accidents. On Earth, that loss is insignificant, absorbed into a massive and forgiving environment. On Mars, you would have to account for every single kilogram. Over the years, those small losses would add up, and you would be forced to mine more and more ice just to break even. So while it is technically true that Mars has water, the statement is operationally misleading. The planet offers you frozen, salty, chemically contaminated ice, often in inconvenient locations, and then forces you to expend a vast amount of energy and hardware just to turn it into something that flows freely from a cheap tap on Earth. Now stack that problem on top of all the others. You need a massive, constant supply of power to mine, heat, purify, and recycle that water. At the same time, the sun is dimmer, dust storms are crippling your solar panels, the nights are brutally cold, and your batteries are struggling to function. The next question is obvious. How do you keep all of this running when the entire planet, from a power perspective, starts with a low energy budget and then actively tries to drain it even further? How do you operate a high-tech human outpost on a world that is, by its very nature, on low battery? On Mars, this is the central problem. Before you can even dream of cities or terraforming, you are already losing the energy game. Let's start with the sun, because that's the first number that works against you. At Earth's orbit, the intensity of sunlight is about 1,360 watts per square meter. At Mars, because it is so much farther from the sun, that number drops to just 590 watts per square meter, a little over 40% of what we get. And that's just the raw sunlight before you account for losses due to atmospheric dust, panel inefficiency, the angle of the sun, or shadows from your own buildings. So if you took a solar farm that could comfortably power a small base on Earth and moved it to Mars, it would suddenly produce less than half the power. To make up the difference, you would have to build an array more than twice as large, spread out over a harsh and dusty landscape. Then you factor in the realities of Mars. The dust settling on the panels, the storms dimming the sky, the extreme cold affecting performance, and you realize that even a massive solar farm will see its output collapse during the dust season. The numbers are blunt. Solar power alone will not save you. Not if you plan to stay for years and build a real settlement. Now let's think about energy storage. Here on Earth, batteries already struggle in the winter. On Mars, the nighttime temperature routinely drops below -80 degrees Celsius. That's -112 Fahrenheit. Batteries despise that kind of cold. Their internal chemistry slows to a crawl. Their capacity plummets and their internal resistance skyrockets. If you repeatedly charge and discharge them in that state, their lifespan will be drastically shortened. This leaves you with two bad options. You can either burn precious energy just to keep your batteries warm inside insulated containers, or you can accept that they will perform poorly and die quickly, forcing you to constantly ship or manufacture replacements. Every kilowatt hour you store is a battle against cold and inefficiency. The energy you store in your batteries during the day has to power your life support, heating, water processing, and communications through the night, while also keeping the batteries themselves from freezing. If you miscalculate, your system can fall into a downward spiral where you're forced to spend more and more energy just to protect the infrastructure that was supposed to be providing you with energy in the first place. This is why the conversation about Mars always turns to nuclear power. A compact reactor, running day and night, unaffected by dust storms, seems like the perfect solution. A few megawatts of steady, reliable power would make life infinitely easier. Heaters would stay on, mining equipment would keep running, Water treatment plants would operate continuously. On paper, it solves many problems at once. But reactors don't grow on Mars. Every component, every kilogram of fuel, every control rod, every spare part has to be built on Earth and then shipped across 225 million kilometers of space. The mass is enormous. The engineering is complex, and your launch opportunities are few and far between. Once a reactor is on Mars, you have to keep it running safely for years, with limited support under a constant assault from radiation, dust, and cold. If that reactor were to fail, your off-world civilization could go from a powered base to a cold, dark camp in an instant. And replacing a reactor is not as simple as rolling up a new diesel generator on the back of a truck. It would mean waiting years for the next launch window, building and certifying a new reactor, and then sending it on a months-long journey across the solar system. You would be betting your entire energy infrastructure on a small number of highly complex machines with long and unforgiving gaps between resupply missions. So you might think, fine, we'll back it up with old-school generators just like we do on Earth. But Mars doesn't give you that option. There is no oil to drill, no coal to mine, and no natural gas to tap. Fossil fuels aren't just absent as a resource, they are absent as a concept. On Earth, a remote outpost can bring in a diesel generator and a fuel tank and have a massive amount of flexible, on-demand backup power. On Mars, there is nothing like that waiting for you underground. You could manufacture your own fuel, for example, by combining carbon dioxide from the atmosphere with hydrogen from water to create methane. But think about what that entails. Before you can produce a single kilogram of methane, you first have to collect water, which we've already established is an incredibly energy-intensive process. Then you have to use electricity to split that water into hydrogen and oxygen. And then you have to run a chemical reactor to combine those gases under precisely controlled conditions. This means you have to spend a huge amount of energy and water up front to create a fuel that, when you burn it, will only give you a fraction of that energy back. So, a backup generator running on locally produced methane isn't free security. It's just another way of converting your already scarce power into a different form. If your electrical grid is already struggling, your water production is marginal, and your reactors are under strain, you are not going to casually divert a huge chunk of that capacity just to make emergency fuel. In the energy department, Mars gives you nothing for free. Every joule is paid for with infrastructure, complexity, and risk. Let's put all of this together. You are on a world that starts with less than half of Earth's sunlight, then periodically blocks that sunlight with dust. It assaults your batteries with long, freezing nights, forces you to ship any serious power source across interplanetary space, and offers you no dense chemical fuels as a backup. Your water extraction systems, your air processors, your heating, your radiation shielding, your mining equipment, and your vehicles all rest on this fragile foundation of power. When that foundation wobbles, everything else follows. A long dust storm hits. Your solar power plummets. Your batteries run colder and weaker. You have to throttle back the heaters. Ice mining slows down. Water production drops. Air recycling margins shrink. The entire life support chain begins to tighten link by link. You don't just lose comfort, you risk crossing a threshold where one more failure cascades into a full-blown emergency. And that leads directly to the most unforgiving part of this entire picture. On Mars, you are not just using power to run lights and tools. You are using it to actively replace the natural systems that do everything for free here on Earth. Your air, your water, your food, your waste disposal, all of it depends on machines running every single hour with no backup from the outside world. So the next question is simple and brutal. What does it truly mean to live your entire life inside a closed life support loop, on a planet where a single broken pump or a contaminated reactor can start a countdown that no one can easily stop? You don't really live on Mars. You live inside a machine, and that machine has to work every second without a break for as long as you are alive. On Earth, air and water are just there. The planet itself is your life support system with its oceans, forests, and weather. You exhale carbon dioxide and plants absorb it. They release oxygen. Rain cleans the air, rivers carry waste away, and the atmosphere buffers small mistakes. On Mars, none of that exists. The cycles that keep you alive are not planetary. They are mechanical. Pumps move air, filters scrub carbon dioxide, chemical reactors split molecules, and bioreactors grow algae to recycle waste. If a single critical valve sticks, if a sensor fails, if a line of code is wrong, you can go from a normal day to a life support emergency in a matter of hours. Let's start with the air. Your habitat must maintain oxygen within a very narrow range. It has to keep carbon dioxide below a critical threshold. It has to manage humidity and trace gases. A single software update that misreads a sensor, a single pump that slows down, a single scrubber cartridge that wears out sooner than expected, and the levels will begin to drift. You won't notice the problem until people start getting headaches or feeling dizzy, or until the alarms finally go off. By then, you are already in emergency response mode. There is no fresh breeze you can let in to reset the system. The air outside is a thin, cold carbon dioxide poison. Your only option is to repair the failing system while breathing the very air that depends on it. It's the same story with water. Every drop in your tanks has been painstakingly mined, melted, and purified. That water is constantly circulating through drinking taps, sanitation systems, hydroponic farms, and industrial equipment. If a filter clogs and ruptures, if the wrong kind of microbes begin to grow in a storage tank, if a chemical pump fails and adds too much or too little of a treatment agent, you can quickly contaminate a large portion of your entire water supply. On Earth, you can just dump a bad batch. On Mars, dumping water means throwing away days of mining and melting work and shrinking your precious reserves. You don't waste water when every single kilogram was extracted from the frozen ground, with a massive energy bill attached. Food adds yet another layer of complexity. If you are serious about living on Mars, you cannot ship all your food from Earth forever. You'll need greenhouses, algae tanks, or bioreactors to recycle nutrients and grow new food. That means a constant supply of light, water, and nutrients, all within a precisely controlled environment. A single plant pathogen, a mold outbreak, a nutrient imbalance, or a failing light fixture could wipe out an entire crop cycle. On Earth, a bad harvest is a local tragedy, but the global food supply can absorb the loss. On Mars, a failed harvest in your main greenhouse is a direct threat to your survival. So why not just bring massive redundancy for everything? Because the physics of getting to Mars is brutal. Every extra kilogram of equipment, every spare part, every emergency supply costs a fortune in launch capacity and has to be planned years in advance. You can't bring a spare for everything. You have to make choices, an extra pump or an extra filter, more reactor components or more medical supplies, more radiation shielding or more greenhouse equipment. Every kilogram is a trade-off, and if you guess wrong, you can't just order another one. The next launch window is about 26 months away, and the rocket you need has to be built, tested, and launched at precisely the right time. To escape this resupply trap, people often talk about bio-regenerative life support, using plants, algae, and microbes to create a closed-loop ecosystem. It's a promising idea, but right now it exists only on a laboratory scale. We have never run a closed system with hundreds, let alone thousands of people for decades, with all the messy realities of human life. The International Space Station recycles water and scrubs its air, but it is still heavily dependent on resupply from Earth. On Mars, you don't have that safety net. If your internal ecosystem crashes, if the delicate balance of gases, nutrients, and microbes in your bioreactors goes wrong, there is no planet-sized reservoir to fall back on. Restarting that system isn't as simple as opening a window. It could mean flushing tanks, regrowing cultures from frozen backups, and replanting entire greenhouses, all while living on emergency rations and bottled oxygen with limited spare parts and a dwindling power supply. In that environment, maintenance is not a side job. It is the very foundation of your civilization. Every pump, every valve, every sensor, every circuit board has to be checked, cleaned, replaced, and calibrated on a strict schedule. On Earth, you can get by with a broken fan for a while because the outside air will leak in and help. On Mars, a broken fan in the wrong subsystem could mean a pocket of stale air, a spike in carbon dioxide, or a dead zone in your greenhouse. So instead of settlers in the classic sense, you would have a team of operators running a planetary-scale industrial plant whose only product is survival. Everyone would be part colonist, part mechanic, and part emergency responder. Your day would be divided between your primary job and the shared labor of keeping the life support, power, and water systems within their narrow operating limits. You would be constantly watching data streams, listening for strange noises from pumps, feeling for vibrations in the ductwork, and double-checking software alarms. Fatigue and human error would inevitably creep in. Someone skips a minor inspection because they're exhausted. Someone silences an alarm to stop the noise and then forgets to reset it. Someone mislabels a replacement filter or fails to properly tighten a fitting during a rushed repair. On Earth, many of these small mistakes are absorbed by a huge and forgiving environment. On Mars, they accumulate inside a closed system where there is very little room for error. An overlooked crack in a pipe can slowly leak precious water into a wall. A miscalibrated sensor can underreport carbon dioxide levels until the symptoms show up in people's bodies instead of on a screen. And that's just the mechanical side. The harder truth is that you are not alone in those loops. Your body, your gut, your skin, your lungs carries trillions of microbes. The same is true for everyone on the crew. In a sealed, recycled environment, those microbes become part of the life support ecosystem whether you like it or not. They will move through the air filters, cling to surfaces, hitchhike in the water, and adapt to the radiation and altered gravity. Over time, they will evolve in ways you cannot fully predict. So the next problem isn't just whether the machines will keep running. It's what happens when human biology, human microbes, and the Martian environment all mix together inside a closed system for years on end. Once you ask that question, you realize that you're not just sending people to another planet. You're exporting entire ecosystems in fragile containers, and you have almost no idea what that will look like after a decade. You think you're sending a few humans to Mars, but what you're really sending are billions of tiny passengers that evolved for Earth and have no idea how to behave anywhere else. Every person in that habitat is not just a body. They are a moving ecosystem. And that ecosystem will react to Mars in ways we don't fully understand. Let's start with your microbiome, the community of bacteria, viruses, and fungi that live in your gut, on your skin, and in your respiratory tract. On Earth, these organisms have adapted to 1 g of gravity, to normal radiation levels, and to a diet based on fresh food. On Mars, you would change all of that at once. The gravity would drop to 0.38 g. The radiation would increase. Your diet would shift to packaged food and hydroponic crops. The air would be recycled over and over. You would touch the same surfaces, breathe the same filtered air, and live with the same small group of people day after day. Your immune system is calibrated to a specific pattern of microbial exposure. Change that pattern, and it can overreact or underreact. Perhaps certain bacteria in your gut will become more dominant when you're eating a diet of processed, shelf-stable food. Perhaps others will die out because you're not getting the same kinds of fiber you did on Earth. This can affect your digestion, your mood, and even your mental health because your microbiome communicates with your nervous system. Add to that the higher radiation levels, which can also damage microbial DNA, and you open up evolutionary pathways we have never seen before. Now think about pathogens in that closed loop. On Earth, a flu virus might spread through a city, but it eventually burns out as people develop immunity and isolate themselves. On Mars, you would have a small crew in a sealed habitat sharing the same air, water, and surfaces. If a virus gets into that system, it doesn't have millions of people to infect, but it also has nowhere to go. It can keep cycling through the same small group, reinfecting people as their immunity wanes, or spreading to new arrivals. The radiation and stress of living on Mars would make all of this even worse. Higher radiation levels can increase the rate of mutation in viruses and bacteria. A pathogen circulating for years among a small, stressed community under constant radiation is in an environment that is actively pushing it to evolve. You could end up with new variants that behave in ways never seen on Earth, with unusual symptoms or resistance to treatment. And you can't just wait for the season to change. There is no fresh air moving in from another continent. No new population to dilute the spread. It's just the same few immune systems over and over again. Then there is the issue of planetary protection. Right now, space agencies go to great lengths to avoid contaminating Mars with microbes from Earth. Probes are baked, sterilized, and handled with extreme care to reduce the number of stowaways. But humans blow that door wide open. We shed microbes constantly, through our breath, our sweat, our skin. The moment you land people on Mars, you are seeding the local environment with life from Earth, no matter how careful you try to be. And the reverse risk is not zero. If Mars has any native life at all, even just hardy microbes in the soil or ice, you would be taking a huge gamble by introducing them into a warm, pressurized, nutrient-rich habitat. They might die instantly, unable to tolerate oxygen or our biochemistry. Or they might adapt and thrive because you've just given them an environment far more hospitable than the cold, dry surface outside. You could end up with new kinds of biofilms, strange forms of corrosion, or interactions with your own microbes that no one could have predicted. You would essentially be running a live biological experiment, 24 hours a day, with your crew and your habitat as the test subjects. There is no pause button. And the data you would need to do it safely, how mixed ecosystems of Earth life and potential Martian life behave over decades, simply does not exist. You would be learning as you go, from inside the petri dish. Now think about what happens when something goes medically wrong. On Earth, if a case is complicated, you escalate. You go from a local clinic to a larger hospital, and then to a specialized research center if necessary. You get access to advanced imaging, expert surgeons, and massive blood banks. On Mars, the best hospital in the world is whatever you manage to pack into a lander and bolt onto the side of your habitat. That's it. If someone needs complex surgery, say a major spinal procedure after an injury in low gravity, you'll have limited tools, a limited blood supply, and maybe one doctor who trained in that specialty years ago. If someone develops cancer, you might have some basic diagnostic tools and a few treatment options, but not the full array of therapies you would have on Earth. For a strange infection, especially one that might involve a mutated microbe from your closed system, you can send data back home. But even at the closest approach, the signal takes several minutes to travel each way. You will never be in real-time contact with experts. Every medical decision would be made on hard mode. You wouldn't have easy access to organ donors. You wouldn't have a large population for clinical trials. You wouldn't have a medevac flight to a better hospital. And the person you're treating is someone your entire small community knows personally. Losing them would be a blow not just to morale but to your operational capacity. Even routine healthcare would become a challenge. Dentistry in low gravity, pregnancy and childbirth at 0.38 G, the long-term management of chronic diseases like diabetes or heart conditions. None of that has a tested playbook. You can extrapolate from data on Earth, but at crucial moments, you would just be guessing. And when you guess wrong, you can't send the patient home. There is no back to Earth tomorrow. The launch windows open only once every 26 months, and the trip itself takes months. So let's layer all of this together. Your microbiome is shifting under new and stressful conditions. Pathogens are trapped with you in a feedback loop. You might be mixing unknown Martian chemistry with life from Earth in ways no one can predict. And your medical system is a small, isolated outpost with almost no room for error. You're not just changing your address from one planet to another. You're changing the entire biological context your body has evolved for, with no real escape route if things go wrong. And all of this is happening while you are living in confined modules, under constant risk, cut off from real-time conversation with anyone back home. Once you account for all of that, you have to face the next layer of difficulty, not in your cells or your machines, but in your mind. What happens to a person when their entire world is a small, dangerous bubble on a silent red planet, and stepping outside without a suit is the same as choosing to die? Even if every machine on Mars worked perfectly, your brain would still have to live with what that actually feels like, day after day, year after year. And that is a completely different problem than fixing a pump or swapping a filter. Let's start with the distance in the most basic sense, talking to people back on Earth. The time delay between our two planets is not a small glitch. It is a fundamental consequence of the speed of light. At the closest alignment, a signal takes about 4 minutes to travel one way. At the farthest, it's more than 20 minutes. So a simple back-and-forth conversation, you ask a question, they answer, can easily take half an hour or more. You don't get real-time phone calls. You get something closer to very slow text messaging with long, silent gaps in between. On Earth, if you're having a bad day, you can call a friend and talk it out. You can hear their voice, feel that live connection. On Mars, calling a friend means sending a message and then waiting. And by the time the reply arrives, your mood may have shifted, the crisis may have passed, or you might not even feel like talking anymore. That lag changes the very nature of support. You're not just far away physically, you are functionally disconnected in human terms. You can send videos, you can get advice, but you lose that immediate sense that someone is right there with you in the moment. Now look at your physical world. Your entire environment is a small collection of spaces, a habitat, a few connected modules, a rover. Outside of that is a surface that will kill you in seconds without a full suit of protective gear. The outdoors is not a place for relaxation, it is an operational zone. On Earth, you are surrounded by effortless sensory variety. Different weather, different skies, different crowds of people, different sounds. You can walk through a park, stand by the ocean, or sit on a busy street all without a second thought. On Mars, most of your sensory input is fixed. You see the same walls, hear the same hum of fans and pumps, breathe the same filtered air, and look at the same small group of faces day after day. Your brain uses variation as a stabilizer. It resets itself based on changing light, changing sounds, and casual contact with strangers. Take that away. Compress everything into a few controlled modules, and monotony itself becomes a stressor. The days blur together. You mark the passage of time with checklists and mission logs. Even if you rotate your tasks, you are still inside the same narrow box, under the same constant background threat that if anything major fails, you are in serious trouble. Then there's the social environment. Put a few dozen people together in a closed space under constant risk and a strict schedule, and you're not just doing engineering, you're running a social experiment. Hierarchies matter. Leadership styles matter. A person with a difficult personality doesn't just annoy you for a few hours and then disappear into a city. They are there every single day, at meals and meetings, during emergency drills. Arguments don't have space to diffuse. Grudges don't get diluted by a wider world. The group's dynamics can lock into patterns that are very hard to break. Stress amplifies all of this. People are working long hours on critical systems. Sleep is disturbed by alarms, by noise, by worry. If someone starts to burn out, you can't just send them on vacation. There are no real weekends away. Small conflicts over chores, schedules, or priorities can grow into major tensions because there is nowhere to step away and cool off. Depression, anxiety, and irritability are not fringe possibilities. They are expected outcomes unless you invest a huge amount of effort in selection, training, mental health support, and clear governance. And remember, everyone knows exactly what is at stake all the time. As you walk through the habitat, you pass by life support panels, radiation monitors, and pressure gauges. You are consciously aware that a major failure in any one of those systems could kill you and everyone you know. That constant background knowledge is different from the abstract risks we face on Earth. Here, the danger is personal, immediate, and right outside the hull. Then there is the hardest psychological trap of all, the lack of a real exit. On Earth, if a job is destroying you, you can quit. If a city feels suffocating, you can move. Even with financial or legal constraints, there are usually multiple escape routes. On Mars, "I'm done, I want out" is not an option you can act on. The launch windows for returning home open only once every 26 months, and that's assuming a return vehicle is fueled and ready, and that the program will even let you leave. So you are locked into the experiment, emotionally and physically. If you discover that you hate the environment, that you don't fit in with the group, that the constant risk is eating away at you, your choices are limited. You keep going, or you break. And knowing that you have no easy way out amplifies the pressure. Problems that might be tolerable for a few months on Earth become much heavier when you realize they could stretch on for years. Put all of this together and you get a very different picture than the heroic poster version. Life on Mars is a tight loop of familiar corridors, slow, delayed contact with home, and a small social circle that never really goes away. It is a constant awareness that the outside world is not your friend. You might be surrounded by advanced technology, but your subjective world can still feel narrow, repetitive, and tense. And that's before you factor in grief, accidents, or long-term health problems. If someone dies in an accident, there is no larger society to absorb that loss. It hits the entire group all at once. And the systems still have to run. Repairs still have to be made. There is no pause button on life support while people process what happened. So even if you solve all the engineering problems, even if you perfect the life support loops and the power systems, you still have a group of human beings stuck in a silent red environment with limited freedom and delayed contact with the rest of their species. The next question then is unavoidable. If that is what daily life feels like on Mars, how much worse does it get when you remember just how far away you really are? How long it takes to travel there and back? And how few chances you get to send help when something goes wrong? Distance is not just a number between two planets. It is a hard limit on how fast you can fix mistakes, rescue people, or change your mind. And Mars sits on the wrong side of that limit. Getting there in the first place is a monumental undertaking. Even with the most efficient trajectory, a one-way trip takes 6 to 9 months. That's 6 to 9 months in a cramped vehicle in microgravity with radiation levels higher than anything on the surface of the Earth, and with no possibility of rescue. If something goes seriously wrong in deep space, no one is turning a ship around in time to help you. The best you can hope for is advice, sent by radio and delayed by minutes, while you try to fix the problem with whatever tools and spare parts you happen to have on board. And remember, that journey is just the beginning. You endure months of risk just to arrive at the place where the hard part really starts. Living on Mars for years. Any plan that talks casually about sending people to Mars has to reckon with the fact that each of those people will spend the better part of a year inside a metal tube, with the same few faces dealing with bone loss, muscle loss, and radiation before they even set foot on the planet. Then there's the timing. Earth and Mars are constantly moving, orbiting the Sun at different speeds. They only align in a way that makes an energy-efficient journey possible once every 26 months. That is your launch window. Miss it and you wait for the next one. There is no, "We'll just launch next week instead." The physics doesn't care about your schedule, your budget, or your crisis. It only cares about where the planets are in their orbits. This has brutal consequences. On Earth, if a remote base runs low on supplies or has a technical problem, you can ship them what they need in a matter of weeks. On Mars, if a critical piece of equipment fails after the launch window has closed, an emergency resupply is impossible. You might be able to send a small, high-speed probe with a tiny payload, but you are not sending tons of food, water, or reactor components on short notice. Fast evacuation is a concept that simply does not exist for Mars. If you wanted to leave outside of the launch window, you would be looking at a very high-energy, extremely expensive trajectory that would not be available as a routine option. Underlying all of this is the concept of delta V, the total change in velocity required to make the journey. To get off the Earth and into space, you have to reach a speed of 11.2 kilometers per second just to escape the planet's gravity. Then you need even more delta V to shape your orbit, rendezvous with a transfer vehicle, and then match orbits with Mars at the other end. In plain terms, sending anything to Mars is incredibly expensive, in energy and hardware and in money. And that is not going to change just because rockets get a little bit cheaper. You still have to climb out of a deep gravity well, cross tens of millions of kilometers of space, and then land safely on another world. Reusable rockets help, but they don't erase the basic physics. Every kilogram of payload sent to Mars represents a long and complex chain of launches, fuel, and careful planning. That is why on a Mars mission, every single kilogram has to earn its place. On Earth, when you design a system, you can over-engineer it. You can add extra bracing, extra redundancy, extra comfort, because the penalty is mostly just cost. On Mars, every extra bolt, every extra chair, every comfort item competes directly with water, food, oxygen, medical supplies, spare parts, and radiation shielding. You want thicker walls on a module? That's more mass to launch. You want more exercise equipment to fight bone loss? That's less room for other hardware. You want more medical gear, more backup computers, more replacement pumps. Fine. But something else has to be taken off the manifest or wait for a later mission. The logistics budget isn't just about money, it's limited by physics. Rockets can only push so much mass per launch, and the launch windows only open at certain times. This constraint affects every single design decision. Do you bring a second air recycler or more spare parts for the first one? Do you pack large, comfortable private cabins, or do you use that mass for a larger storm shelter with better radiation shielding? Do you send more people for social stability and productivity, or fewer people with more equipment per person? On Earth, you can often solve a problem by just shipping more stuff later. On Mars, you have to solve most of those problems up front, in the design phase, because there is no guarantee that later will arrive before something critical fails. Even building up infrastructure is a slow process. If you want to build a serious base with multiple habitats, vehicles, reactors, and factories, you're not going to do it in 1 or 2 launches. You're talking about a campaign of missions spanning a decade or more, with each one delivering another batch of modules, machines, and supplies, and each of those missions will be limited by mass, timing, and risk. If a single key cargo ship is lost on the way, you don't just lose the hardware. You lose the exact pieces that the entire architecture was depending on. So Mars is not just another continent, where you can ship containers by sea and planes by air. It is a moving target on the other side of interplanetary space that only aligns with you at specific intervals, with a deep energy barrier in between. That barrier turns logistics into one of the main factors shaping what is even possible. It squeezes your margins, stretches your timelines, and forces you to make harsh choices long before a single human ever sets foot on the surface. Now add this final twist. When people are confronted with all of these obstacles, the thin air, the cold, the gravity, the radiation, the dust, the distance, their instinctive response is, fine, we'll just change the planet. We'll terraform Mars. We'll make it more like Earth. That sounds like a clever workaround until you look at the numbers and realize that on any human timescale, Mars doesn't bend. The idea of turning it into a backup Earth isn't just optimistic, it's a myth. Terraforming is the part of the Mars story where people usually relax and say, it's fine, we'll just fix the planet. But when you look at the actual numbers, that idea falls apart fast. The option to fix Mars is not really on the table, not on any human timescale. Let's start with the most popular plan. Warm up the planet by pumping more carbon dioxide into the atmosphere. The logic is simple. CO2 is a greenhouse gas, and Mars has a lot of it locked away in its polar ice caps and in the soil. So just melt it, release it, and thicken the atmosphere to trap more heat. The problem is there just isn't enough of it. Studies of the Martian poles and soil show that even if you could somehow vaporize all the accessible carbon dioxide, you wouldn't get anywhere close to Earth-like pressure. You would get, at most, a few tens of millibars. For comparison, the pressure at sea level on Earth is about 1,013 millibars, so you would still be at a tiny fraction of one atmosphere, still in near vacuum territory. You wouldn't get lakes and oceans, you wouldn't get stable liquid water, and you definitely wouldn't be strolling outside in a jacket, breathing without a mask. Walking around unprotected would remain in the realm of science fiction. And even if you could somehow cheat and import extra gases, dumping manufactured greenhouse gases or nitrogen from somewhere else in the solar system, Mars has another built-in problem. It can't hold on to a thick atmosphere. The planet's magnetic field is weak and patchy. It doesn't wrap the entire world in a protective bubble like Earth's field does. This means that the solar wind, a stream of charged particles from the sun, can interact directly with the upper atmosphere, slowly stripping gases away into space. We've actually seen this happening in data from orbiters. Mars has been losing its atmosphere for billions of years, and the process is still going on. So any terraforming effort runs into a fundamental problem. Even if you spend centuries releasing gases into the atmosphere, you're doing it in a system that leaks. It's like trying to heat a house where the windows are always cracked open and the front door never fully closes. You can keep pumping more heat in, but you will always be fighting a constant drain. On a human timescale, this means that any thick atmosphere you manage to build would have to be actively maintained. Stop the effort, and the planet would slowly slide back toward its natural state of thin, cold air. Then there is the problem of timescale. Geoengineering an entire planet is not the same as tweaking a local climate or restoring a forest. You're talking about changing the composition, pressure, and temperature of an entire world, and then stabilizing those changes against ongoing losses to space. Realistic models put that kind of work on a timescale of thousands to millions of years of sustained effort. For reference, most of the civilizations we study in history lasted only a few hundred years. Modern industrial civilization, the only kind capable of even thinking about terraforming, has been around for maybe 2 centuries. So when people say that we'll terraform Mars, they are casually proposing a project that is 10 to 1,000 times longer than any system we have ever built and any continuous technological tradition we have ever maintained. You are betting that your descendants, through wars, collapses, cultural shifts, and technological changes, will continue to pour energy, resources, and attention into the same planetary scale project for a period of time that from our perspective is almost geological. There is no evidence that humans are capable of that kind of focus, and a lot of evidence that we are not. Because of this, the fantasy quietly shrinks. Instead of "we'll make Mars like Earth," it becomes "we'll build domes." You put up giant transparent structures or you bury your habitats under the soil and you call that terraforming. But that isn't changing the planet, that is building a chain of high-maintenance spacecraft glued down to the surface. Under a dome, you still need pressure walls, life support, water treatment, power, and radiation shielding. You still have to manage dust, leaks, and equipment failures. You've just increased the volume you have to maintain and given yourself more surface area for problems to arise. The red desert outside is still just as deadly as it was before. The air is still thin and toxic. The temperature swings, the dust storms, and the radiation are all still there, waiting just a few centimeters away. Just dome it sounds like a simple fix, but it actually amplifies the risk. A small habitat with thick walls is easier to shield and easier to monitor for leaks. A giant glass-like dome is harder to protect from impacts, harder to shield from radiation, and harder to repair if a part of it fails. One structural crack in the wrong place, and you have a huge volume of pressurized air suddenly trying to escape into a near vacuum. That is not a gentle failure mode. And none of this changes the fundamental reality that Mars does not give you the free services that Earth does. Even under a dome, you are not breathing a regenerated planet-scale atmosphere. You are breathing air that is being pushed around by fans and scrubbed by machines. You are drinking water that came from ice mining rigs and treatment plants. You are eating food that was grown in artificial soil or hydroponic trays. The basic conditions outside the walls remain hostile. You are not settled in the sense that people mean when they talk about living on Earth. You are stationed, like being posted indefinitely to a remote, dangerous base. So the honest picture is this: terraforming Mars into a true second Earth is beyond us for any time frame that matters to you, your children, or their children. The planet will not be turned into a blue-green world with open seas and breathable air, not in centuries and probably not in millennia. What we can do is build more or less sophisticated life support bubbles on top of or underneath a frozen, thin-aired, radiation-exposed desert. And even if you accept that, even if you say, fine, we'll live in those bubbles and treat Mars as a permanent outpost, there is more to worry about. The ground you're building on is not perfectly stable. Mars looks quiet, but it still shakes. It still shifts. And it still gets hit from space more often than Earth does. The next layer of problems isn't just above you. It's under your feet, and it's falling out of the sky in the form of rocks you will never see coming. Mars looks calm in photos, frozen, empty, harmless. But that's an illusion. The planet is still moving, still reshaping itself in slow, sharp ways that matter a lot when your entire survival depends on fragile structures sitting on that surface. Let's start with Mars quakes. The InSight lander has detected quakes up to around magnitude 4. On Earth, that's not a big deal. Most people would barely notice. But Mars is not covered in thick soil and deep, weathered rock. Much of the surface is rigid, brittle regolith and fractured rock. When it shakes, even modestly, you can get landslides along the rims of craters and the walls of canyons. So if you decide to build into a slope for radiation shielding, or put your infrastructure near a steep feature for convenience, a small Marsquake can still trigger a mass movement that undermines your foundations or buries your hardware. You also have to remember that your structures are pressurized shells. On Earth, if the ground shifts a bit under a house, you might get a crack in the wall or a broken pipe. It's annoying, but it's not instantly lethal. On Mars, a slip in the ground that twists a habitat ring or a tunnel entrance can stress the seals, open up microfractures, and eventually cause a leak. The regolith doesn't absorb motion the way softer soils on Earth do, so more of that energy can end up in your supports and anchors. When you're designing foundations there, you're not just thinking about static load. You're thinking about what happens when the entire base gets a quick jolt through brittle ground. Now let's shift scale and look at the constant small motions across the surface. The dust devils. These are little vortices like tiny tornadoes that race across the landscape, lifting dust and sand. Individually, they're not dramatic. They're not going to throw rovers into the air or tear off solar panels, but over the years, thousands of these small storms will add up. They will scour the paint and coatings off of your equipment. They will sandblast exposed surfaces. They will move sand into new drifts and hollows. This means that anything you leave sitting outside is in a slow-motion erosion test all the time. Dust devils also rework the very ground you're trying to treat as solid. Paths that were clear can develop new ripples and small dunes. Shallow trenches can fill in. Cables you thought were buried deep enough might get exposed in spots and then buried again, shifting as the regolith creeps around them. Landing pads will gradually roughen as particles are lifted and dropped. You can't just survey a site once, build, and then assume it will stay the same. The surface is constantly changing, and those details matter when you're landing rockets or driving wheeled vehicles with tight safety margins. Layered on top of that is the seasonal frost cycle. Mars doesn't just have water ice. It also has carbon dioxide that freezes out of the atmosphere at the poles in the winter. Each year, CO2 and water frost are deposited on the ground and then sublimate away as the seasons change. This means that the amount of solid material at or near the surface changes cyclically, and with it, the local pressure and ground stability can shift. Over time, this can destabilize slopes and undermine your foundations bit by bit. Imagine building a long pipeline or a row of habitat modules on ground that year after year has ice forming in its pores and then disappearing. In some areas, the regolith can puff up slightly when the ice forms and then settle when it vanishes. A process similar to frost heave on Earth, but now involving both water and carbon dioxide ice. Your structure might not collapse suddenly, but you could see slow, tilting, differential settling and strain on its joints and connectors. Over 10 or 20 years, that's enough to push things out of spec, especially when you combine it with thermal expansion cycles and dust erosion. Now look up at what's coming in from space. Earth's atmosphere is thick enough that most small meteoroids burn up as harmless shooting stars. Tons of space rock hit our atmosphere every day, and almost all of it vaporizes before it reaches the ground. Mars doesn't have that protection. Its atmosphere is too thin to generate the same level of friction and heating. That means that more of those rocks make it all the way to the surface. Most of these are small, not dinosaur killer events, but they still matter. A small impact that would have been a streak of light in the sky on Earth can become a real crater on Mars, throwing debris in all directions. If that happens near your base, you could get rocks hitting your habitats, your solar farms, your antennas, or your vehicles. Even if nothing critical is hit directly, the shockwave through the ground can jar your equipment, and the ejecta can add yet another layer of dust over everything. Over the decades, as you place more hardware across a wider area, the odds go up that something significant will get hit, or that an impact will alter the terrain in a way that your original maps no longer capture. You can't assume the surface is a static platform. It's more like a slow, random hazard generator. Tie all of this together, and the picture becomes clear. Mars is not a friendly, frozen museum where you can set up delicate equipment and trust the ground to stay still. It has quakes that can shake the brittle regolith. It has slopes that can give way. It has dust devils that will slowly sand away your assets. It has frost cycles that will quietly twist and lift your foundations. And it has a thin sky that lets more space rocks reach the surface than you're used to. So, what does that mean for long-term construction? It means over-engineering everything. It means deeper, stronger foundations, more flexible joints, and redundant seals. It means regular surveys of the ground with radar and other sensors to spot changes before they turn into failures. It means spreading out your critical systems so one impact or landslide doesn't take out everything at once. It means budgeting for a level of inspection and maintenance that makes even the harshest environments on Earth look easy. And all of this is on top of the hostile air, the cold, the radiation, the dust, the power problems, the biological issues, and the psychological pressure. You are spending an enormous amount of engineering effort just to stand still, just to keep a small population alive on a planet that doesn't want to host you. At that point, you have to ask a different kind of question. If the physics, geology, and logistics make life on Mars this fragile and this expensive, what does that do to the economics and the ethics of sending people there in the first place? Are you really living on Mars, or are you just surviving in an extremely high-cost laboratory? And what does it mean to ask people and their children to sign up for that? By now, it's clear that Mars is not welcoming you. So the next hard question is this: if surviving there is that difficult, who pays for it? And what exactly are they buying when they send a human being to live in that environment? Let's start with the raw cost, because physics turns into price very quickly. Getting 1 kilogram from the surface of the Earth all the way to the surface of Mars isn't cheap just because rockets have become reusable. By the time you stack up the costs of launch, transfer, braking, and landing, you're still talking about tens of thousands of dollars per kilogram, even with very optimistic assumptions. That's for anything: a wrench, a bag of food, a battery. Now scale that up to one person plus everything that person needs to not die. A human is not just 70 or 80 kilograms of mass. Add their share of the habitat, the life support hardware, the radiation shielding, the food, the water, the suits, the tools, the medical gear. You're quickly in the range of tens of thousands of kilograms per person. Multiply that by tens of thousands of dollars per kilogram, and each colonist represents a multi-billion-dollar logistics package just to get started. And that's before they've produced anything and before you factor in resupply, replacements, or emergencies. That alone flips the idea of a cheap frontier on its head. On Earth, new towns can grow because the basic environment is free. You put up buildings and run some pipes, and the air, the rain, and the soil are already working for you. On Mars, every kilogram that makes life possible has to be bought, built, and thrown across space. The planet doesn't give you free infrastructure. You either ship it or you fabricate it from scratch, with machines you also shipped. Then comes the part most people don't like to think about. You never stop paying the maintenance bill. Cities on Earth eventually become economically self-sustaining. They import and export goods. They repair their roads with local asphalt. They build new hospitals with local industry. A Martian settlement has no such base to start from, and it may never fully achieve one. Every pump, every filter, every circuit board, every seal in an airlock has a lifetime. It will fail. And the high radiation, the dust, and the constant thermal cycling will probably shorten that lifetime compared to Earth. When something fails, you either replace it with a spare you brought with you, or you manufacture a new one on Mars. But manufacturing complex components locally means building factories which themselves need machines, raw materials, power, and people to run them. You've just turned keeping people alive into building and maintaining a growing chain of industry in the harshest place you've ever tried to live. In practice, this means you would be stuck in a hybrid mode for a very long time. Some things you could fix or print locally, but many others would still need to be shipped from Earth on a schedule tied to the launch windows. A critical pump, a specialized microchip, a reactor part, a medical device. These are not easy things to bootstrap from raw Martian rock. So the stream of cargo would keep flowing every 2 years, with each shipment carrying high-value items the base needs simply to maintain its current level of capability. Miss a few of those resupply missions because of a major technical problem or an economic crisis on Earth, and that maintenance chain starts to break. The settlement wouldn't just coast along gracefully, it would begin to degrade. Some systems would go from fully functional to barely functional. Redundancy would be lost. Safety margins would shrink. The idea that a Mars city will just stand on its own 2 feet the way a terrestrial city does ignores the fact that the planet itself is not providing any of the background support. The maintenance line never ends. Now let's bring ethics into this. You're not sending robots, you're sending people who feel pain, who form relationships, who have children. You are asking them to live in a place where failure is brutally unforgiving. One major system collapse, power, air, water, radiation shielding, could mean a mass casualty event, not just an inconvenience. A mistake in design or management doesn't just give you a bad quarter. It can wipe out an entire community in a matter of hours. Is it ethical to encourage people to sign up for that, especially if the plan quietly assumes that some of them will never come back? A one-way mission means a person is committing not just to work far from home, but to die there. And once children are involved, the questions get sharper. A child born on Mars doesn't choose 0.38 G higher radiation and a world where walking outside unprotected is lethal. They inherit it. Their bones and organs might adapt so strongly to Martian conditions that Earth's gravity becomes dangerous for them. Are we comfortable creating a group of humans who may never be able to safely visit their ancestral planet? There is also the issue of consent over time. Someone in their 20s might willingly sign up for a high-risk one-way life on Mars. But what about that same person in their 40s after a decade of dust storms, hardware failures, and health issues? There is no easy way to say, "I'm done, send me home," when the launch windows are 2 years apart and return vehicles are scarce and expensive. You're locking people into an experiment whose parameters can shift under their feet. while their ability to exit remains tightly constrained. So you have to be honest about what Mars really is in this picture. It is not a clean escape hatch from Earth's problems. It is not a backup Earth sitting there waiting to be claimed. It is an extraordinary, dangerous laboratory for learning how life, technology, and societies behave on another world. Treating it as a refuge from climate change, war, or resource scarcity is backwards. If we fail to keep the Earth habitable, Mars will not save us. Moving from a damaged Earth to Mars would be like walking out of a leaky but heated house in the middle of winter and climbing into a broken refrigerator. You might be able to rig a heater inside the fridge, but you're still in a box fighting the outside environment every second. From a scientific and exploratory point of view, a small, carefully supported human presence on Mars might be worth the cost and the risk. We would learn things we simply cannot learn any other way. But calling that a new home for humanity is misleading. It's more honest to call it what it is: a permanent survival experiment on a hostile planet with a price tag so high and a risk profile so sharp that only a tiny number of people will ever experience it directly. So when you hear the line, "Mars is where we'll go if we ruin the Earth," the answer bluntly is no. Mars is where a few of us might go to understand just how narrow the window for human life really is. For everyone else, and for any serious future for our species, the planet that actually matters is the one we are standing on right now. This video is presented for educational and entertainment purposes, and the information provided should not be taken as professional advice. If you found this analysis valuable, please like the video and subscribe to the channel for more explorations like this one.